Thank you very much. Again, my name is Avrahami. I'm from FX Palo Alto Lab. I'll be telling you about the effect of edge targets on touch performance. And as soon as my remote control starts working, I guess I'll use space. All right. Oh, this is just showing here. Sorry, I borrowed someone's Mac so I can show it. Okay, so edge targets on desktop mousing environments are known to afford fast reaction time. For example, we know that in Macs, typically the control panels or the menus are at the very bottom of the screen, at the very top of the screen, and they even have options for assigning the corners of the screen for very quick access to certain functions. So the research question that this paper tried to tackle is what happens with edge targets on touch devices? Are they advantageous as they are in desktop environments? Are they harmful to performance? Or do they play no role in target acquisition? So I'd like to start with a small exercise with everybody. So I'll show you a point on the screen. Imagine that you're touching it. So if you don't mind pointing towards that target. Okay, imagine that you're tapping on it. All right, and then I'll show you a target, and you need to try and hit it as fast as you can. All right. Okay, so are you ready? That's what the participants did in the study. Ready, go. Ready, go. Ready, go. All right, let's change something. Let's move the tablet. Okay, are you ready? Go. And again, go. All right, so I have a question for you. Which performance would be faster, hitting this target or this target? Again, is it this one or this one? If we think specifically of Fitts' law and our reaching ability, if the target or the closest to the edge plays no role, then both of them should be exactly the same, right? So again, the research question is, are edge targets on touch devices advantageous to performance as they are in desktop environments? Are they harmful, or does the proximity play no role? So a bit of background. There's been a lot of research on human performance in desktop mousing environments, and a lot of work also specifically about the benefit of edge targets. Because what we know is that if there's a target along the edge, it allows us to do this very gross motion, or in the words of affordances, offer a lot of amplitude tolerance. We can just move the mouse quickly or the pointer quickly, and we'll stop at the edge of the screen. There's been work from affordances that showed that edge targets, which they called semi-infinite space, allowed people to be up to 44% faster. And actually this phenomenon was also used in other systems where they said we can just block, let's say, a stylus at the edge of the screen or an edge of some frame to allow a user, for example, with some accessibility problems, to be able to have better performance at hitting targets. So, for example, the work by Warburg et al. Or by Froelich et al. When we move from mouse or stylus to touch environments, we see a growing body that tries to analyze, and we've seen a few papers already today, trying to understand human performance in these environments. And I want to point out specifically one piece of work by Perry and Arcade that looked at what happens when you're trying to reach targets, especially edge targets, in a one-handed kind of, they used some PDA, you hold it with one hand and you try to reach it with your thumb. Now, one issue that I think doesn't generalize particularly well is that we know that the thumb is constrained. Reaching something that's far away will be slower and harder with the thumb. So what happens when pointing is not constrained by the physical reach of a thumb? What happens when the screen has no bezel, as most touchscreens today are? So I'll tell you about two experiments that try to tackle this question. And the first experiment tries to understand the impact of being close to the edge, irrespective of the distance of the target from the user. So the first hypothesis basically says that we'll reject the null hypothesis. It says that being close to the edge will have an impact on performance. Now you can immediately think of some reasons why it will help performance and some reasons why it will hurt performance. So I'll also list two sub-hypotheses here. The first one, which is H1A, says that independent of distance, the proximity to the device edge will make your response faster. And the second one is the converse, says independent of distance, the proximity to the device edge will hurt your performance. Okay? So I said that we want to study the proximity to the device edge independent of distance from the user. How can we do that? What I did was I used a very large surface and printed a very thin frame that looked kind of like an iPad mini, one layer to put on top of the device, and that allows me to move the frame around but know that I'm presenting the exact same target to the users. So this is what it looked like. You can see where basically I'm simulating a tablet underneath on that large screen, and there's this single target can be in different locations. So this is what it looked like. There were 3 locations for the frame. Let's call this location A. And it had these targets that users had to hit. They would always start from a ready button outside the device and reach in, or it would be in position B, and you see that there's some overlap already, or in position C. So these were all the targets that the users had to reach. And specifically, you can see that a number of them are in the area of overlap, and I highlighted in orange the ones that are in some cases a corner target and in some cases a center target. All right. So 12 participants completed 504 trials each, and when I say a trial, I mean the same thing that you guys did earlier. Hit the ready button, and then I measure the time it takes them to hit the target, the distance that they take, and the offset from the center of the target. And they all completed 3 blocks, 1 in each frame position. So let's go into the results. First, a high-level result, looking just at air, basically hitting outside the target, or even just looking at the offset from the center of the target, there was no effect of the proximity to the edge. And that allows us to use all the trials now in the rest of the analysis and just use the offset from the edge as a covariate. And the second effect, which we expect from Fitts' law, is that distance had an effect on speed. So that's good to know, and we have to include distance in the analysis of the effect of proximity to the edge. Now, if you remember those 3 orange targets that I showed you before, if we analyze those targets specifically and say, did being a corner target or being a center target have an impact on performance, we see that the effect was very large. There was about 100 millisecond difference. It was highly significant. And seeing that difference allows us, first of all, to accept hypothesis 1, basically say, being close to the edge has an impact. It also allows us to accept hypothesis 1b that said that being close to the edge will hurt performance, and reject the hypothesis that said it will help performance. Now, if we look at all the targets that were in the experiment and code each of them as whether it was a center target, an inner target, an edge target of different kinds, or a corner target, we see that performance degraded basically from being a center target to inner target, and every single one of those pairwise comparisons is significant. So here on the left side, you'll see the non-edge targets, and you can see that they're significantly faster than targets along the edge of the device. So we saw that performance degraded when targets were close to the edge, but there are still some open questions that this raises. For example, would that happen also not in this setup that I showed you? Would this happen when someone is holding a tablet in their hand and tapping? What would happen if we used large targets and not just small ones? Or for example, can we start moving targets away from the edge to get the effect to go away? So in order to analyze that, I ran experiment 2, in which I investigated the, now we know, a negative effect of edges with different target sizes and with different gaps between the targets and the edges. So we have 2 hypotheses now. The first one says that large targets should not be affected by the edge because it's just much easier to hit them. And the second one says that we can remove or reduce the effect by moving targets away from the edge. So this is what the experimental setup looked like. This time people were holding a device in their hand and tapping targets. The ready buttons this time were on the device itself, and when the gaps were introduced, the ready buttons were also moved in the same way, in the same distance. So to test the effect of target size, I used 2 target sizes this time, 11 millimeters targets, the same as in experiment 1, and 22 millimeter targets. Just for comparison, if you look at the iPhone 6, for example, and you look at one key on the keyboard, the dimensions are 5 millimeters by 7 millimeters. So those are relatively large compared to many targets that we interact with on a daily basis. And the second thing, to test the effect of introducing gaps, I used 4 different gaps between the targets and the edge of the display. 0 millimeters, which would be a complete edge target, 1.5 millimeters, 4 millimeters, and eventually 11 millimeters, which was the closest we had to non-edge targets in this experiment. I also threw in another condition, because I could, which was to see if having the device in 2 different orientations would make a difference. And I can tell you already that that had no effect on any of the results. Okay, so again, 12 participants, each of them completed 384 trials, and the trial again was from reaching the ready button until you hit the target. Measured the time, the distance, and the offset from the target center. There was one thing that was a bit tricky, is that there were 2 separate blocks. One is that the ready buttons were at the bottom and you had to hit upwards, and one was when the ready buttons were at the top of the display and you had to hit downwards, and that was just because people might obstruct their view of the ready buttons otherwise. Okay, so let's look at the results of experiment 2. Again, proximity to the edge had no effect on error or on touch point offset. There was lower error rate for larger targets, which is not that surprising, but that again allows us to include the offset from the target center as a covariate in the rest of the analysis. And the second thing was that if we look specifically at those targets that were as far away from the edge as possible, the 11 millimeter targets, and those that were on the edge, we can see that there was a significant effect. So that just confirmed the results of the first experiment. So moving away from that setup that I showed you before to a handheld tablet did not remove the effect. So when testing the effect of target size, we see that large targets, first of all, are significantly faster than small targets, and that's something that we'd expect based on Fitts' law. But, and that's very interesting, large targets with 11 millimeter gaps were significantly faster than large targets with the smaller gaps. And that means that even when the target is larger than a normal finger, it still has an effect. Being close to the edge still has an effect. So that actually forces us to reject hypothesis 2 that said that for large targets it would not have an impact. Although I have to say this is only for those 2 sizes. If the target was the size of half the screen, then we would probably see that effect go away. Now if we look now at the effect of adding different gaps between the target and the edge to see if maybe just allowing you to see the target better would make a difference, we see that just adding a 1.5 millimeter edge gap between the edge and the target did not improve performance. However, as soon as there was 4 millimeter gaps between the target and the edge, there was already an improvement. And what I plotted here for you is if you look at what the difference in gap does in the top left and the bottom right targets, you see that adding even small gaps between the target and the edge starts improving performance. So we can only partially accept H3 that said that adding the gaps would make the effect go away, but in some cases it does. So one of the key, so we found an effect, right? But the question is, why does it happen? And that's a really tough question. Is it a physical thing? I think the answer is clearly no, because we know on these tablets that we have today that there's almost no physical edge to the screen, right? Some tablets are completely bezel-free. Is there a visual interference? At the end of experiment 1, I had a conversation with quite a few people, and we were discussing what could be the cause of the effect. And one of the things was that maybe it's hard to separate the target from the edge. It blends into this one big object. But if that was the case, then adding these gaps, even very small ones, would make the effect go away, but it didn't. Could it be that there's an issue of global and local processing? Is it that we have a 2-stage processing where first we locate the target, the large target, which is the tablet, and then we move from the center of the tablet and try to locate the target? That could have been the case in experiment 1, where first you locate the frame and then you locate the target within it. But in experiment 2, everything was happening within the context of the tablet itself. So that's probably also not the reason. Could it be that we just have some weird preference for the center of displays? Maybe, but there was a recent study by Firestone and colleagues where they asked people randomly on the street to tap on different shapes on a tablet. And people tapped everywhere, not necessarily in the center of the display, but also around the corners. Could it be that we have some fear of going out of bounds or drawing outside the lines? Right now, it's my best guess of what's going on, but I think there's a lot of room to explore further what's causing the effect. But just knowing that there's this effect can already give us a few implications for practice and design. If efficiency is important, if we're trying to design an interface that is efficient, then putting targets on the edges of the display means that we should probably make them larger, or that we should introduce some gaps between them and the edge to improve performance with them. And another thing that's very interesting is that there's a lot of work that tries to improve our performance with targets by increasing their effective size in a way that is invisible to the user. However, those two experiments suggest that what's happening here is completely cognitive, that we are slowing ourselves down on the way to hitting a target. So doing things behind the scene may not help. So to conclude, edge targets on touch devices have a negative effect on performance, and it's exactly the opposite effect that edge targets have in a desktop mousing environment. So if you're going to have an operating system that is designed for a mousing environment run on a tablet, these things that you thought would be extremely efficient for users might now become the least efficient. We saw that the effect persisted for large targets, which was surprising, but that moving targets away from the edge improved performance in some cases. So I just want to point out two limitations of the work which we should think of as areas for future work. The first one is that you rarely see an interface that just has one target that you need to hit. Typically you have many targets and many distractors, right? So the question is, what happens when an edge target now has fewer distractors, just because you can draw fewer things next to it? Would that actually help edge targets over inner targets, for example, as in this example? And also, it will be interesting to investigate what happens when you know the position of a target ahead of time. So if I know that the save button is going to be in the top right or the done button is going to be in the bottom left, does that help me with my performance? If you're interested in any of these possible future experiments, come talk to me afterwards. Thank you very much.
About the visual distraction, I was wondering if you played at all with background color, if you were using like a black bezel to use a black background, or I saw with the plastic red iPad looking thing you had a white background, it looked like.
Great question. When I created experiment 1, I created a set of, I think, 12 variables, and eventually I constrained them. And then the question was, at the end of experiment 1, do I go into these variables, or what are the things that would help, I would say, cut down as many of the possibilities to help us understand what is happening. But definitely going to inverse display configurations, I think, is extremely interesting and needs to be done. I agree.
And then also, if you do that, going back to the original experiment and using a virtual frame instead of the plastic frame, so that you can have literally the same color for the background as you do the bezel, might be interesting to look at.
Right.
Hi, Joe at the University of Toronto. On the second experiment, you didn't mention error rates or false positives on hitting the edges. Seeing that you have an effect, did you see any of those?
So in the second experiment, the error rate overall was 3%, and it was significantly lower for large targets, but there was no effect of being close to the edge or of any of the gaps on performance.
Thank you.
Thank you.